Hello everyone, my name is Wilson Zarate. The name of the dissertation is Generative Design of Modular Industrial Architectural System. It was made in conjunction with the company Casais in Portugal. Well, the first point is try to understand some of the problems that the construction industry has in this moment. And one of them are the latent of lack of productivity, some discontinuity of the flow of the information from one stage to another, mismanagement of some resources, and lack of clarity on the repercussions of the decision made, especially the initial design phases. So the dissertations try to make some points in the mixture between building information modeling and how it could apply to prefabrication systems in order to optimize the resources, the taking of decisions, and to allow greater organization in the construction area. All this was developed also with a case study that was proposed for the company Casais that I will explain in some minutes. The main objectives of the dissertation was first to create a methodology that allows the integration of prefabrication system development with building information modeling, especially the characteristic of automation technologies in the conception on the face of the project. To create an easy integration and communication of the different stakeholders in this stage, and in order to create an easy to use product that allows with the minimum input obtain relevant information about the project in order to take more objective and better informed decisions in the beginning of the project. Until develop for the case study a configurator that allows to obtain automatic design models with related feasibility data to be later evaluated and developed. The methodology developed was first the analysis of the literature involving building information modeling in relation with generative design and the prefabrication construction. Then the comparative analysis on some digital tools related with configurators. Then the proposal of a methodology with some of these tools that were selected in order to create a configurator for the case study. Fourth, the development of a computational model, and fifth, a validation of this computational model to create the configuration in relation with the case study. This is the structure of the dissertation. It was divided in 4 parts. As I mentioned, the first part is all the state of the art in literature and the state of the art of some tools that are available in the market at this moment. Then some definitions about the framework, the methodology to use, and the case study. And from them to create some parametric schemes and to develop the key performance indicators that are like the main objectives of data to reach to the configurator. And finally, the implementation of the computational model. First, well, the research was about how the prefabrication works in the construction industry. Then we developed some main benefits about the use of prefabrication in the constructions. It could be highlighted the reduction of noise, the increase of cost predictability, the less dependency in weather conditions, reduction in time, reduction in construction waste, opportunities for standardization, and increasing quality in products. Some characteristic of these prefabrication systems and modularity, that is basically the use of modules as a unit to define the conformation of the entire building, and the use of processes like DFMA, that is design for manufacture and assembly, that is the consideration on the designers for the requirements of the manufacturing and assembly stations in the initial stages of the process, especially in the design phases. This is a comparative analysis made by a study in Canada that compared the schedule of a traditional construction system in comparison with the prefabrication system. So it could reach until the 20 or 50% of more productivity at the end of the project. Then being applied to prefabrication, there are several benefits in each one of the phases of the projects. It could be highlighted, especially in the design phase, to increase the quality of the designs. It allows detecting the existing collision between different components, improve also the evaluation and correction of some issues. And in relation to this dissertation, it was especially important to make use of the parametric characteristic of building information modeling in order to automate some design processes to generative design and make decisions based on more objective information related to key performance indicators with the use of configurators. Another aspect that is important now in the prefabrication industry is the use of mass customization. That is basically searching for a high level of productivity, but maintaining some level of flexibility. And in this context, the use of some tools like the configurators start to have a high importance. A configurator is a software with logical capacity to create, maintain, and use electronic product models that allow the definition of all possible options of a product and the variation in combination with a minimum of data as input. In this way, the configurators could help to improve the usability with people that doesn't have the professional skills of designers or engineers. It was taken as a reference, especially in study of Cow and Hall, some authors that develop a classification of the configurations, and they divide them in three typologies, depending on the target of the phase of the process of the construction that they reach. Typology 1 is for the concept design, typology 2 for the design stage, and typology 3 for the detailed design stage. Then after making this reference, we started to analyze some of the tools that are available in the market in relation to configurators. In this case, it was Shapediver, iPar, TestFit, Plan Finder, Speckle, and Rhino Compute. And after analyzing all of them, we arrived at some conclusion about which one of them could be useful to use in a configurator to create like a methodology for specifically the case study. This is like a table comparing some of the benefits and the typology of each one of them. And we propose this framework, like a general framework to develop a configurator. Basically, it's using Rhino Compute as a remote server, with Grasshopper as a API to create the computational model. It could produce a web browser to allow the definition of the configurator, and the idea is to connect Rhino Compute with Revit through a platform that is called Speckle. This dissertation focused just in one part, that is the creation of the configurator in the part of the computational model, and as an alternative use human user interface that is a plugin for Grasshopper to create a user interface. Then the start analysis to the case study, the prefabrication system. But basically, this one has like 6 main elements: the foundation and vertical cores, the last panels that are the modules that basically define all the configuration of the projects, the glulam columns that are wood columns that are around the building, steel and concrete middle girders that are the beams, steel and concrete composite columns that are columns inside the buildings, and the external walls that are in the facades. This is some analysis of each one of these elements. The different configuration of the columns, how the internal elements are joined together. After the analysis of the case study, it was proposed the parametric schemes of all the relationships of the parameters in the systems to start to analyze the computational model. These are all the elements that were analyzed in relation to each one of the elements. And in the cases where we have like a compound shape, how to divide the shape in relationship with the configuration of the slabs. Then it was defined some key performance indicators, that is basically the information to get from the configurator. This is the workflow definition. It was divided mainly in three parts. The first one has all the computational model. The second part is the development of the user interface, and the final part is the development of the exporting data. The computational model was divided in 17 steps to produce the final model. All these are is one of the 17 steps developed in the computational model. These are just graphics. It was all developed in Grasshopper. For the user interface, it was divided in three windows. The first window is this one that contains all the parameters divided in 3 steps. The second window contains some graphics and tables, and the third step window contain the a 3D model. This is the parameters of the user interface, all the parameters. These are the 2D views implemented in the user interface. There are the 3 steps of the user interface. This is how it looks, the first window of the user interface with the parameters and the plan view divided in three steps. These are the graphics that are generated automatically from the model. These are the tables generated also automatically. And finally, this is the tree view, the tree window that produces automatically the building with all the elements described. Finally, this is the part of the configuration that is for the data export. So it was decided to export the data into formats, all the inputs and outputs in format for Excel, and the 2D views, the graphics and 3D view in formats for JPG format, in order to be used in the future for another configurations. And this is basically the computational model developed in Grasshopper. I have a small video. Sorry, the parameters that were established.
We lost your sound. I don't know if it's just in the side.
Yeah, this is the second step. So we have the direction of the slab. You can decide which one of the direction in more detail here in the second step. The movement of the course. The third step, it was established some extensions for the course to modify the size of the course in some directions, some spacings for the course and the slabs, and some parameters for the columns. Then you can create the graphics and tables automatically for this model with the slab quantities, column quantities, all the areas, and the quantities of the facade modules, and the tables automatically also created. Each of the modules and all the elements, and the 3D view. And in the configuration, you can decide also it's divided by elements, so it could be turn on and turn off is one of the elements. And finally is the exporting of the data. So you can decide if the inputs, outputs, 2D views, 3D views, or graphics to say.